let's start the recording. So the book comments that the Markov chains Markov chains, and you'll see why they call them Markov chains. The Markov chains described in this section, section 4.9, are used as mathematical models of a wide variety of situations in biology, business, chemistry, engineering, physics, and elsewhere. Okay, and so this example that I'm going to let you copy down here is a very nice example that will incorporate many of the ideas in section 4.9. So let me give you a moment to copy the example down. Okay, so let's talk about this now. All right, so we have here a city-suburb migration matrix, and it's a very simple matrix. You know, we have two categories: the city and the suburbs, and you know, we could be even more complex. We could have city, suburbs, like country. You know, we could be like living out in the country. We could have more categories, but I want to start off with a simple example. Let's see here now. What do you notice the columns of this matrix add up to? I mean, the numbers in each column, what do they add up to? That's right. Good, Ben. They add up to 1. That's right. Why would that be? Why would that be? What are these numbers, 0.95, 0.05, 0.03? What do they represent? These numbers in this migration matrix. Like 0.95. Ah, that's right, Nafani. Very good. They represent percentages. They represent probabilities. And so this matrix that you have here, okay, is called a stochastic matrix because the columns are what are called probability vectors. So let's interpret this. 0.95, the 0.95. Okay, 0.95 means there's a if you live in the city, then there's a 95% chance after 1 year that you're going to stay in the city. That's what that 0.95 means. Okay. On the other hand, if you live in the city, there's a 5% chance that you would move to the suburbs after a year. You see that? On the other hand, if you live in the suburbs in this city, and they don't mention the city, whether it's DC, New York City, but for this city, if you live in the suburbs, there's a 3% chance you'll move to the city. But if you live in the suburbs, there's a 97% chance that after a year you'll stay in the suburbs. So going from suburbs to suburbs is the same as staying in the suburbs. So the transitions are, you can go from city, you can move from you can move, well, let me write this the right way. If we were to draw like a little picture here, okay, where we have a city and we have suburbs, you can move from the city to the suburbs. You can move from the suburbs to the city. You're allowed that. If you live in the city, you can remain in the city. If you live in the suburbs, you can remain in the suburbs after, this is after a year. So this is a pictorial representation of the migration matrix. We just don't have the probabilities written in. Does it make sense that, let me ask you this. Does the trend seem to be people are, like over time, what's the trend going to be of movement? Are people trending towards going to the suburbs or trending towards going to the city? That's right, Justin, the suburbs, that's right. And that makes sense because the probability, if you live in the city of moving to the suburbs, that's 5%. Whereas if you're living in the suburbs, the probability that you would move back to the city is only 3%. Okay. So, and it seems too, based on the matrix here, that the probability that if you live in the city that you'll stay in the city, that's 95%. But the probability if you live in the suburbs that you'll stay in the suburbs, that's 97%. Why do you think the probability higher that once you live in the suburbs, you're going to stay in the suburbs. Why do you think the probabilities are a little higher? Well, Justin's right. Rent is wild in the city. Okay. What could there be other reasons? Right, Benjamin, you have a family, okay, or you're retiring. I mean, but certainly the family, if you have a family, it's cheaper to live in the suburbs than living in the city. So this matrix, they're putting in probabilities that make sense. Are there any questions so far? Okay, who's comfortable so far? All right, Eleanor is, and maybe in one more thumbs up. If we could have one more thumbs up, I'd okay, thank you, hon. All right. So again, this matrix M here is what's called a stochastic matrix. Okay, I took a whole course on stochastic matrices in graduate school. Stochastic matrix is a matrix whose columns are probability vectors. And we also say that M, the matrix M, is also called a regular matrix. Okay, because if you were to, a regular matrix means if you take the matrix and you raise it to some power, eventually you'll be able to find a power large enough so that M to that power would contain all positive entries. So like for instance, M to the first power is equal to M. Okay, and that's all the entries are positive. But you could, for instance, have you could have a 0 in one of the spots, say. But if you take the matrix M and raise it to a high enough power, like maybe the 10th power, maybe then all the entries would be positive in that M to the 10th power. So that's what a regular matrix means. It just means essentially, a regular matrix means that essentially after a certain number of time transitions, you can get from one state to another state. That's essentially what it means. In this case, the states are the city and the suburbs, but you can have a big matrix that has a lot of different states. Okay, states are categories. Okay, so in a regular matrix, eventually, after a certain number of time transitions, a certain number of years, a certain number of months, you can reach one state from another state. Okay, for all the states. Now we have some questions here. If initially 60% of the population live in the city and 40% of the population live in the suburbs, let's focus on part A here. How will the population be distributed then in the region after 1 year, after 2 years? Okay, well let me show you how you would do this. So solutions. And we'll go back to B and C, but let's talk about A here. So for solution A, what I did was I just wrote a little picture of the migration matrix, and it turns out that matrix multiplication is going to be very important here for understanding what's going on. We were asked, how will the population be distributed after 1 year? Well, and we're assuming that initially 60% of people live in the city and 40% of people live in the suburbs. So the way you find out then after so I call that x sub 0. That's called x sub 0. So that's what's called a state vector. Okay, the vectors are state vectors. Okay, and initially, 60% of people live in the city and 40% of people live in the suburbs. We want to know after 1 year what percentage of people live in the city, what percentage of people live in the suburbs. So I call that then x sub 1. Okay, x sub 1. That's your state vector after 1 year. And to find the percentages, you just take your migration matrix and you multiply it by your state vector x sub 0. Or we can call it a probability vector as well. Now there's a lot to copy down here. Let me give you a moment to copy all this down, and then I'll go through it with you, okay? Please let me know if you have any questions. Okay, please let me know if you have any questions. See, what I do in class, of course, if we were like on campus, I would write this on the board and sort of talk as I go. But I think it's with the remote learning, you have this in front of you. I think it's easier just to copy it down and then I talk about it. At least give you a chance to copy it down. Okay, so give you a few moments here. Okay, so, all right. So you know how to multiply matrices. Okay, and so of course, I'm going to take the first row here in the matrix M and multiply it by the x sub 0 vector, and that will give me the first entry for x sub 1. So remember, I'm taking a 2 by 2 matrix, that migration matrix, times the probability vector, which is a 2 by 1 vector, and I'm doing that so I can find probabilities, the probabilities that, like what percentage of people are going to be in the city and the suburbs after 1 year. Well, that's 2 probabilities, so of course I'm going to get a 2 by 1 matrix. So why did I multiply the matrix M times the vector x sub 0? Well, let's think about that. How, what are the ways in after 1 year of time a person can be living in the city? Well, one option is that if you are in the city, you stay in the city. Well, if 60% of people are in the city, living in the city, 95% of them stay in the city. And so that's 0.95 times 0.60, 95% of 60%. That'll give you the percentage of people who are in the city after, that'll give you the percentage of those 60% of people that are still living in the city after a year. On the other hand, okay, if you live in the suburbs, you can move to the city, right? If you live in the suburbs, you can move to the city. Well, 40% of people initially are living in the suburbs, and of the 40%, 3% of them, or I should say, yeah, that's right, 3% of them are going to move to the city. And so you take 0.40 times 0.03. Okay, so in other words, well, what's 3% of 40%? What percent of that would be, of the 40% of people, I want to be a little bit careful here. Hold on. Of the 40% of people living in the suburbs, 3% of them will move to the city. So that means that contributes 1.2% of the 40% move to the city. Okay, are there any questions on that? Okay, so you can see kind of I have the headings here, like right above what they go with, Okay, now let's talk about the bottom entry. So, okay, 40% of people live in the suburbs initially. So we want to know, well, after a year, what percent of people are going to be in the suburbs? Well, of the 60% of people that live in the city, 5% of them move to the suburbs. So that would be 5% of 0.60. 5% of 0.60, which is 3%. Okay, so of the 60% of people living in the city, 3% of them move to the suburbs. Similarly, of the people in the suburbs, 97% of them stay in the suburbs. So if 40% of people are living in the suburbs, 97% of them stay in the suburbs. And so this is how you compute the percentages of people living in the city and the suburbs after a year. How many think this matrix multiplication, how many see it as a very, I mean, this idea of how you multiply two matrices, the row column rule, how many are seeing the value of it in terms of interpreting how to get these percentages. Okay, there. Thank you, Justin. It is useful. It is absolutely useful. Thank you. And so now, if I may move to the next page, we're going to get our answers. Okay. So then, all right. After 1 year, well, if you compute, compute this here, what do you get? 0.90. Oh, well, no, I actually have it down here, don't I? When you multiply m times the vector x naught, x1 is going to be 0.582. The vector x1 is going to consist of entries 0.582 and 0.418. Okay, so that means after 1 year, 58.2% of people will be living in the city, and 41, or I should say after 1 year, 58.2% of the population will live in the city, and 41.8% of the population will live in the suburbs. Okay. And that is mentioned right here. Now, what about after 2 years? How are we going to find after 2 years how the population is distributed? Well, to find x2, you just take the migration matrix and multiply it by x1. Or you could think of that, since x1 is m times x sub 0, x2 could also be thought of as m squared times x sub 0. And when you multiply that, you're going to get 0.565 and 0.435. And so this means after 2 years, 56.5% of the population will live in the city, and 43.5% of the population will live in the suburbs. So think what's happening here. Who should be worried about losing population over time? The city or the suburbs? Who should be more worried here over time? That's right, the people in the city. And this is important. This kind of analysis is important. Okay. I mean, I want to know if I'm going to build a business in the city, if I'm going to, build a McDonald's or an Olive Garden restaurant or a Starbucks coffee. If I'm going to construct it in the city, or rent a space in the city for my business, I want to know over time, how's the population going to be changing? Is it going to be changing? If so, how much? I mean, this is valuable, important information. How would you find the population distribution after 10 years? How would you find that? Something times something, right? Okay. Well, m to what power times x sub 0 times the initial population distribution. That's right, m to the 10th power. That's right, Nafani. Hung, you're comfortable with that? Excellent, excellent. Okay, all right. Well, now Are there any questions so far? Okay, then let's go back to the handout here. The example. Now, in part B, we're being asked in part B, what percentage of population will eventually live in the city? So, do you think it's possible that the population will stabilize over time, the population distribution between the city and the suburbs? If there are no other, like, the migration matrix, the values here come about based on observation, records, city records, suburb records, okay. But if nothing changes, like over time, and these percentages in the migration matrix remain the same, do you think it's possible that the population distribution between the city and the suburbs might stabilize, might reach an equilibrium? Nafani thinks so. And intuitively, that is correct. I mean, it is true. It is true that the city is losing. I want to say this the right way. Hold on. Let me just check one thing. I actually just thought of something. One moment. One moment, class. It is true that the city is losing residents, losing a percentage of its population every year. But if you notice, and don't worry about that page there. If you notice that after one, like the city population started off at 60%. After 1 year, it dropped to 58.2%. That's a drop of 1.8%. Then, after 2 years, the city population dropped from 58.2% to 56.5%. That's a drop of how much? 58.2% to 56.5% is a drop of what percent? What percent drop is that? Going from 58.2% to 56.5%. That's right. Good, on 1.7%. So the first year, the population of the city dropped from 60% to 58.2%. That was a 1.8% drop in population. The second year, the population of the city dropped from 58.2% to 56.5%. That's a 1.7% drop. So that drops a little less after the second year. The first year, the population drop in the city was 1.8%. But then in the second year, the population drop was 1.7%. So the population's dropping, but it's dropping less. And the third year, it's going to drop. It'll drop again, but even less. So the point is there should be, at some point, a stabilization. Okay, a stabilization. All right, and so it makes sense, this question makes sense here to ask what percentage of the population will eventually live in the city, eventually. The question is, how do we find it? How do we find that population? Well, okay, one way is to take M, okay, times x sub 0 and raise it to a very high power, like maybe raise it to the 100th power. So that means we're finding the population distribution of this region, city and suburbs, after 100 years. And you're going to get you're going to get, some probabilities. Then what you could do is you could take the migration matrix M and raise it to the 101st power and multiply it times x sub 0. And again, you'll get some percentages for your distribution of population. You'll get some percentages. But if the percentages here are equal to the percentages here, then you basically, if that's one way of finding these stable percentages. Okay. In other words, we want to find what the steady state vector is, the steady state vector, the steady state percentages. How many have heard of steady state in like differential equations, for instance, or one of your other classes? Okay, Nafani's heard of it. How many have heard of steady state? I know more of you than Nafani's heard that. Benjamin's heard of it, and Hung's heard of it. Okay, well, we have it here with Markov chains too. The question is, the problem is doing it this way. Doing it this way is labor intensive. I mean, how are you going to know when to stop? How are you going to know when to stop? You have to the two entries have to be the same. The two percentages have to be the same for you to know when you've reached steady state. So even though numerically this intuitively makes sense, we want to find another way to get these values. And so the answer to part B is if there's a percentage of the population, and we'll call it that will eventually live in the city. So this vector Q is my steady state vector. If there's a percentage of the population vector Q that will eventually live in the city, that means the vector Q has to satisfy this vector equation. M times the vector Q has to equal the vector Q. When that happens, you found your steady state vector. Because remember, anytime you take the vector of percentages, your population distribution is contained in this vector, right? And when you multiply that vector, and we're calling it vector Q, but if you multiply that vector by M, that means after the population distribution of Q doesn't change after 1 year. If you take the vector Q and multiply it by the matrix M, and you get back the vector Q, that means that your population distribution has not changed after 1 year. Okay? And so you've reached a steady state. So it's much better to find the steady state vector Q doing this. Now, well, okay, what do we got here? We got M times Q equals Q, and we want to solve for that. So the vector Q, I'm going to write it as the identity times the vector Q. Okay, and then I'm going to subtract I times Q over to the left, and I get this result here. All right, let me give you a moment to just, I just want to give you a moment to catch up here. Let me know if there are any questions up to here. Okay, so, all right, what we have here, right here, is well, we have a homogeneous system of equations. Okay, we're going to solve this augmented matrix. Okay, and since M is a regular and stochastic matrix, and they will be that way for section 4.9, then that means M has a steady state vector Q. That's by theorem 18 in the textbook, and I'll let you refer to that. So now we have to find the steady state vector. And the steady state vector Q is going to tell us what percentages eventually, after many, 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 many years, what percentage of the population will live in the city, what percentage will live in the suburbs. All right, may I move to the next page? Are there any questions so far? Okay, Nafani's good. Okay, then I shall move forward if everybody's good. So this is just a matter then of solving, an augmented matrix. All right, and the matrix M consisted of entries 0.95, 0.05, 0.03, and 0.97, and I'm going to subtract from M the identity matrix. Well, we know the identity. We know the identity matrix. We know the identity matrix. We know its entries. And this is a very simple matrix to solve. There's no need to pull out MATLAB. Okay, no need to pull out MATLAB here. What did we get here? We have two equations. We have right here, we have two equations that are the same equation. Two variables, but really just one equation, right? Because these two equations here are the same equation. So what's that mean we're going to have? If we have one equation, essentially one equation with one equation and two variables, what's one of the variables going to have to be? Good, that's right. Free variable, that's right, Nafani. And so, very good. And so, but I don't want to mess with these decimals. So what I'm going to do is I'm going to take 1 divided by negative 0.05. Well, obviously what I did here was I took row 1 and added it to row 2 and put the result in row 2. And then what I did here was I took row 1 and multiplied it by 1 divided by negative 0.05, which is going to be negative, 20, I believe? Yeah. And put that result in the first row. And then I get nice fractions. Well, my MATLAB likes fractions, right? And so now I have that x2 is free and x1 is 3/5 times x2. Because remember, we have an augmented matrix here. Okay, give you a moment. Let me know if you have any questions. Okay, now, so let me ask you this. Could x2 is free and x1 is 3/5 x2. So could I say, okay, let x2, let's say let x2 equal, I want to be a little bit careful here. Let x2 equal 5. And then if I did that, x1 would be 3/5 times 5. And that's equal to 3. And so my vector q, now I'm not saying this is right, I'm just putting this aside. x2 is free. Okay, let's say I let x2 equals 5 and x1 equals then going to be 3/5 times 5, which is 3. That means my vector q will consist of entries 5 and 3. Is that okay? Is that an acceptable answer for my steady state vector of probabilities, of percentages? No. Why, Benjamin? Why is this not okay? Percentages should add to 100. And I think, Haley, you're thinking the right way along with Benjamin. We're talking percentages here, or we need decimals that will add up to 1. Okay, so that our percentages add up to 1. So even though x2 is a free variable, because you are working in this application, x2, the free variable just can't be anything. It's like the chemistry problems when you balance the chemistry equations. You have to you set your free variable to equal to a certain value. So what we're going to do is I'm going to write the vector x here and parametric vector form. And this is very helpful because I got to figure out what is my free variable going to be. What value of x2 is going to be such that my vector x, I'm calling it vector x because I don't call it vector q yet because I don't have it yet. I have a vector x. That's a general vector. Vector q is a vector that has probabilities in it. So how am I going to choose this x2? How am I going to choose this x2 so that my entries are probabilities? Well, by factoring the x2 out, writing that vector x in parametric vector form, you notice you have a 3/5 here, and you have a 1. So if you just let x2 equal 1 divided by 3/5 plus 1, you'll get 5/8. So that'll always work. Take 1 and divide it by the sum of these entries. Okay. And so the vector q will equal 5/8 times 3/5 times a vector with 3/5 and 1 in it, that's going to get you 3/8 and 5/8. Up here, by the way, I show why this process always works. Okay. Okay, I show why that process. If you take any vector, if you choose your free variable, if you have a vector with A and B entries, and you choose your free variable as 1 over A plus B, then you're going to get entries that will add up to 1. You'll get probabilities. So this shows why it works over here on the right. So, okay, this means then that the vector Q has entries 3/8 and 5/8. This means then that 3/8, eventually over time, 3/8 or 37.5% of the population will live in the city over time. And this is something actually that, you know, I mean, I'm sure you've heard that New York City, okay, there's great concern in New York City that people are, you know, leaving New York City. They're migrating out because of high taxes, for example. You know, how do they determine this kind of thing? Through like this kind of process. You need to have a migration matrix. So I don't know. Over time here, in our example, for our city, eventually, if the migration matrix stays as it is, over time, 37.5% of the population will live in the city. So maybe 20 years from now, 50 years from now, and that could be, you could sort of figure that out by taking m to the kth power and changing the k. But the point is, over time, the population right now, which was, you know, initially the population of the percentage of people living in the city was 60%, and in the future, we see that population, that percentage dropping to 37.5%. So the question is, are you happy about that? Would somebody be, if somebody's going to build a Starbucks in the city, is this okay? Is this here a risk that you know, the owner or the business person would be willing to take? And this kind of thing determines where businesses build their stores and so forth. They don't just build, you know, a McDonald's, you know, over there in Olney for no reason, right? There are studies that are done to determine this kind of thing. How many think this is absolutely fascinating? I mean, how many think this is like, I mean, this application of linear algebra, how many think it's pretty cool? All right, thank you, Eleanor. I love hearing that. I love hearing that. I'd sure like to see a few other responses. I'm not forcing you, but gee, you know, who thinks, wow, you know, what I learned today is pretty cool. Okay, Samantha's liking it. Thank you, Samantha. Naima, thank you. Thank you, Catherine. Nafani, marvelous. Excellent, excellent. All right, thank you, Abby. Appreciate it, appreciate it. Thank you, Ariana. Wonderful, wonderful. Are there any questions at all? I'm going to stop the recording, and I know our class time is done. Let me stop the recording. Are there any questions?